Welcome to the SPE podcast, powered by the Society of Petroleum Engineers. You're listening to SPE Live, Generative AI Implementations on Spatial Data. The audio from this episode was previously recorded on May 22nd, 2024.
Welcome to this SPE Live on Generative AI Implementations on Spatial Data. My name is Yusuf Falola. I'm a PhD student in the Department of Petroleum Engineering at Texas A&amp University. I'll be your moderator today. Today's session is going to last for about 30 minutes, and we encourage you to ask questions throughout the event. It's now my pleasure to introduce our guest. Dr. Misra is an associate professor at Texas A&M University. He is a researcher and educator in the field of subsurface monitoring and forecasting for the exploration and production of subsurface earth resources. Dr. Sid has published 2 books and developed 9 technologies related to machine learning and electromagnetic sensing for energy and earth resource exploration. In 2018, he received the U.S. Department of Energy Early Career Award, and in 2020, he was honored with 4 international awards for his contributions to exploration geophysics and petroleum engineering. Dr. Sid holds a Bachelor of Technology degree in electrical engineering from the Indian Institute of Technology, Bombay, and a PhD degree in petroleum engineering and geosystems engineering from the University of Texas at Austin. Dr. Sid, welcome to this SPE Live.
Thank you, Yusuf. Glad that I'm talking to you early morning over here. Thank you.
Yeah, sure. You're welcome. So let's get started by discussing some examples to illustrate how is Gen AI being used by engineers and scientists in our field today.
Great. Generative AI is all about creating new data that has similar characteristics with the training data. One simple example for all of us to relate to is, let's say you want to create a great music on guitar. How will you do it? You will go collect, let's say, 100 popular songs. You'll try to understand the rhythm, the pattern, the chord progression. And then once you learn these basic elements, the secret sauce behind good music, you will combine them to create your own new music. So that's what generative AI helps us achieve. So in terms of use, a lot of the uses are very new. It's a very new field. A lot of things are developing. There are excitement. There is some hype. There is some successes. So as engineers, how I see generative AI being used, I see them being used in 6 areas. Number 1 is engineering design. Let's say you want to create a bridge. You want to create a bridge under a cost constraint, a material constraint, and you want the bridge to have a certain aesthetics, a certain style. For such purposes, for engineering design, to explore the design space, generative AI is a very good tool. The second use case for engineers is material discovery. Now we talk about energy transition. We need batteries. If you want to create batteries that are stronger yet lighter, what composition, what elements should you combine together to create such a battery? Such problems can be solved through generative AI. Generative AI is being used for finding metal organic framework that can help us purify water, that can help us capture CO2, capture methane. So all these material discovery is where engineers are using Gen AI. Now, one use case that I'm seeing plenty often within energy companies is data summarization. What I mean by that is various oil and gas companies, engineering companies, they have a lot of historical data, a lot of reports, a lot of projects, a lot of emails. So they try to use generative AI to process all this historical data. Gen AI can relate reports with each other. It can relate reports between projects, between multiple years. So it gives you this holistic perspective of how decisions were made. With such a system, with a data summarization system through generative AI, engineers can ask questions. For example, whenever an operation was changed, how much production increase or decrease happened? Such questions can be answered through this holistic processing of data over multiple years, multiple projects, and so on. Now, the final 2 areas or final 3 areas where I see a lot of Gen AI applications by engineer, one is code generation. I see it personally. A lot of young engineers, they use generative AI to generate codes that can help them do rapid prototyping, proof of concept. If they want to do some data visualization or data analytics in a particular way, they implement Gen AI. A lot of engineers use Gen AI for product design. What do I mean by product design? It can be a software product, a hardware product, but when we design a product, we want the product to interact seamlessly with user. As the user is using the product, we want to capture the data. So for such streamlined operation, automated workflows for product design, Gen AI is a pretty good tool. It helps us improve user interface. It helps us improve user experience. And the final use case that I see for a lot of engineers is they use Gen AI to create edge cases. When they generate new edge cases, they can test their hardware or software for presence of bugs, for presence of failures. So all these failure analysis of various hardware and software systems can be speeded up, automated through generating edge cases, edge test cases with Gen AI applications. Just kind of my final words on Gen AI used by scientists. Scientists use it to create new hypotheses, to detect anomalies, because in these anomalies, there may be new signs. A lot of scientists are using Gen AI for molecular discovery. They create molecules that can go to a particular target and perform a particular task. So a lot of use cases, a lot of exciting use cases, but some of them are very new. Let's see where the forefront evolves as the time progresses.
Yeah, thank you, Doctor. You've really shared a lot of insights, examples from civil engineering to the energy industry. So let's move ahead to our next question, which is, now let's just go deeper into understanding the foundations of Gen AI. What do you think are the key principles, techniques behind Gen AI?
So I'll try to break the principles into 3 steps. So Gen AI, the word is very fascinating, but it has 3 steps. And these 3 steps are done over and over again. Step 1. Step 1 is to understand what is the basic secret sauce, or what is the basic building block in the data. What makes a cat image look like a cat image? What makes music from Spain sound like music from Spain? So for that, we have to understand the basic building block. For example, you enter a house. When you enter a house, you can look at a room and you can say this room is a kitchen. You can look at another room and you can say it's a bedroom. Why? Because you know the basic building blocks present in these rooms. So that is step 1. The algorithm tries to find the basic building block in the data. Step 2 is the algorithm quantifies the relationships between various building blocks. What I mean by that is, let's say we have a knife. Whenever there's a knife, there has to be a cutting board. Whenever there is a duck, there has to be a water nearby. So this is the quantification of basic building blocks in the data. So that's step number 2. And how it is quantified? It is quantified in terms of probability distribution that helps us understand the order in which these basic building blocks are arranged and their relationships, their conditional probabilities between the building blocks. And the final step is the generative step, where the algorithm combines various building blocks to create new data. And this new data that is created has to be similar to the training data. That's the whole objective of Gen AI. Now, Gen AI is implemented in 6 different approaches. That is what I came across, 6 different approaches. The first one is generative adversarial networks. This is a very old concept in the sense I have come across generative adversarial networks for the last 10 years. So it's a pretty old concept. So what's the goal in generative adversarial network? There are 2 neural networks. You can imagine one to be a composer, a music composer, and the other to be a critic. The music composer composes music, and the critic says, hey, this music is outdated. This is not new. So the composer keeps on improving. It tries to create new and new music, and the critic keeps on telling the composer whether the music is new or it's outdated. So this is a competition between 2 entities, and through this competition, through this adversarial effect, the network learns, or the composer learns to create new music. That's approach number 1. The second approach is variational autoencoder. Variational autoencoder is again an old concept where the data goes through filters. It goes through multiple filters, and as it goes through filters, the data is compressed. When the data is compressed, we identify the basic building blocks. Once we understand the basic building blocks in the relationship, then generative tasks can be performed. So that's variational autoencoder. The third task is, or the third approach of generative AI is autoregression. Now, autoregression is pretty simple. You have an image, there's a pixel. This pixel is related to pixels around it. So you can use the information from pixels around it to predict what is present in that pixel. This is called autoregression. Whenever there's a duck, there will be water. Whenever there's a mountain, you will see the sky and the cloud. So this is what autoregressive methods do. They try to find relationships within the particular image. So I told you 3 approaches: GANs, VAE, autoregression. The fourth approach is recurrent neural network. What recurrent neural network does, it processes a sequence. By processing a sequence, it finds the basic building blocks and it finds how they are arranged, what's the relationship between them. A good example would be if you give recurrent neural network a Western music, it will identify that there's a particular piano sound, there's a particular violin sound, and this is what makes the Western music sound the way it is. The fifth approach is very new. This is transformer. The transformer is the powerhouse behind a lot of ChatGPT, Google Gemini applications that we have come across. So what is a transformer? Unlike RNN, which is looking at one sequence, a transformer looks at parallel sequences. It does multiprocessing, and through this multiprocessing, it tries to identify the building blocks and the relationship within a sequence, between a sequence, and that's how it helps us perform the generative task. And the final very interesting generative AI use case that I've seen over the last 3 years is called diffusion. This is an approach to Gen AI, diffusion. What is diffusion? You have a good data. That good data is made noisy. As the data becomes noisy, the diffusion algorithm figures out how the data changes when noise is added. Through that, what the diffusion network understands is how to denoise to create the good data. So it learns the noising and then the reverse of noising, which is denoising. Through that, the diffusion network can take noise and generate new images, new audios, and has shown a lot of potential in the generative tasks. So I hope I answered your question. What is the principle and the 6 approaches that I came across for generative AI implementations?
Sure, you did. Like you've shared so much knowledge in the past few minutes, from telling us about the key 3 principles and also like different ways that or different techniques you can use for Gen AI purposes, from GAN to diffusion. I'm hearing diffusion for the first time today, so I'm also taking that back to go and do more research. So thank you so much. Let's go to our next question, which is, can you just tell us how you have used Gen AI on spatial data for engineering tasks? This is now more related to your own field.
Yeah. So in this particular work where we use Gen AI, you were also involved in this particular work. And this work was done with an energy company where we wanted to speed up geomodeling. So what is a geomodel? A geomodel is a realization of the subsurface. Now, in the subsurface, there's a lot of uncertainty. We don't know exactly how the porosity is distributed, where are the channels, how the channels intersect. So there's a lot of uncertainty. That's why we don't have just one representation of the subsurface. We have multiple representations of the subsurface that represent the various probability distributions in which the subsurface can exist. Permeability, porosity, saturation, phases, anisotropy, and many more properties, right? So this is a geomodel. A geomodel is a 3D representation. It represents the property distribution in a statistical fashion. In this work, we use Gen AI to speed up geomodeling. What I mean by that is we want to create this 3D geomodel in a very fast way. We want to speed up that entire geomodel generation process. For this, we use Gen AI. And as I mentioned, Gen AI uses 3 steps. So the first step for us was to find the basic building blocks. And the second step was to quantify the relationship between the building blocks. So for the first step, which is to find the building blocks, we used something called variational autoencoder. There was an advancement that was done on variational autoencoder through the help of Yusuf and some other researchers in our team, where they brought in vector quantization with variational autoencoding, which was originally developed by Google. So they took that entire framework, they applied on training geomodels. When they applied it on training geomodels, they found the basic building blocks. These basic building blocks, you can imagine it to be a vector that has 10 numbers, 10 integers. So this is a way for you to understand what this basic building block is. So our team found these basic building blocks. These are vectors. Our step one is done. In step two, we used autoregression. What does autoregression does? We have a vector which has 10 numbers. We wanted to understand conditional probability between these different numbers. Once we understand the conditional probability between these numbers, we are understanding the probability distribution of these building blocks. So for that, we use autoregression. For each given element in that vector, how will the number show up depending upon the past numbers? That is what conditional probability is. Once we quantified that, our third step is to mix match these basic building blocks based on the quantified probability distribution to create new formulations of the building block. So that's where we are going into step three. For step three, what we did, we used this autoregression algorithm, which has quantified the probability distribution. From these probability distributions, we can sample these basic building blocks. So they represent whatever we learned from the training data. And the final step was to take these basic building blocks, run it through a decoder. Where does this decoder come from? The decoder comes from the variational autoencoder that we applied in the first step. So we run this basic building block through a decoder. The decoder takes the basic building blocks and generates the entire 3D geomodel. This entire approach, the training, the testing, it took us, let's say, close to 1 to 2 months to figure out the right architecture. Once we figured out the right architecture, once we designed the system, which took us another 2 to 3 months. So in total, 6 to 8 months of work was invested in creating this entire workflow. Once that is done, our entire geomodel generation process happened in seconds. We can generate 1,000 3D geomodels within 1 minute, which is very fast. And the geomodels that we're generating, they represent the subsurface. You can imagine them to represent, let's say, 1 kilometer by 1 kilometer by 100 feet thick reservoir. So that is one example where we used generative AI on geomodels and spatial data.
Yeah, thank you so much for giving us that example. I think that is something a lot of our audience would understand better, because I believe they are more familiar with the subsurface. So,
yeah. So now, Yusuf, what I want to know from you, because you were involved in this work, you were very heavily involved on the encoding side of things, where we wanted to find out the basic building blocks. You have worked on a lot of deep neural networks, large models. So tell me, from your experience, when you create these networks to work on spatial data, or let's say spatio-temporal data, what kind of challenges, what kind of limitations do you face in getting these advanced AI methods to work with spatio-temporal data? Share your experience, Yusuf.
Yeah, so that's a very good question, and I'm going to answer that generically under three major headings. One would be in terms of the data set, secondly in terms of the model itself, and third would be some other issues. So, and this response will be generic on the challenges we face in our industry in working with spatial temporal data with Gen AI models. So talking about the data sets, I believe everyone will agree with me. The first issue we have is unavailability of data. For Gen AI models, you need a lot of data sets to train them for them to be able to work appropriately. So the unavailability of data is the number one challenge. But personally, one challenge I've also encountered related to data sets is the size of these spatial data sets. So as data set can be so huge. In one of my projects related to CO2 forecast, CO2 storage forecast, I have a data set with just 250 samples, but the size of this data set is about 11 gig. So 11 gigabytes, the day-to-day PC is not going to be able to run it. So I had to use a PC with about 250 gig RAM to be able to process this data set and actually run the model itself. So that's another challenge that we face working with spatio-temporal data. Thirdly, will be the time it actually takes to generate the data set is another issue, because in my own case, to generate one sample takes me like an hour. So imagine if you want to generate 1,000, so you need like 1,000 hours to generate your data. So that's a lot of time. So that's another challenge that we face working with spatio-temporal data and including and training them with GenAI models. Then lastly, related to data set is that we all know that the geology everywhere is different. So if you develop a model using a geology of, let's say, Texas, for instance, you have to try to either train another model if you want to apply, if you have to retrain the model if you want to apply it to a data set in Norway, for example. So in that case, although you may do something called transfer learning that can help you fast track this process, but that's definitely another challenge. Next, talking about the models itself, the first thing is the complexity of the model, which goes back to the computational cost I talked about earlier. So some of these models cannot run on the day-to-day PC. So you definitely need PCs with high storage capacity, high RAMs to be able to run train your GenAI models on this data set. Secondly, I would say that in some cases, our data set are sparse. For instance, in my own case, I'm predicting CO2 saturation, so which means that the CO2, its migration in the subsurface it only covers a few space compared to the large subsurface area. So it means all the other areas will be zeros, for example, and then you have values in only a few specific areas. So these sparse data sets are always trouble for AI models to be able to predict or even learn from. So that's another challenge that I think that we face training GenAI models on our own spatio-temporal data. Lastly, talking about other issues, I think these are general issues in our industry. One is the privacy concern concerning data sets. So companies hardly share data set due to privacy concerns. So, and that limits the amount of data available for us to train these GenAI models on. And lastly, I'll mention that the acceptability of machine learning AI in our industry, I'm not sure it's so high, the percentage, because even when you train your machine learning model AI models, like the execs, they'll still want you to tell them, give physical examples on how this thing works for them to be able to accept your results, make decisions based on what you have done with this model. So I think these are some of the challenges I feel we face in our industry, applying GenAI models on spatio-temporal data.
Yeah. So thanks, Yusuf, for that. We have 8 more minutes. So maybe what we can do is I can kind of conclude our discussion and then we can move on to Q&A. So for concluding the discussion, I just want to reiterate what you mentioned, the challenges, and especially challenges related to creating GenAI models on spatial data. Now, when you talk about GenAI, right? ChatGPT, Google Gemini, these are the most popular. How much time, how much effort, how much data went into creating these systems? For example, if you just talk about a large language model, it takes somewhere around 10 million books. It has to learn from 10 million books. That's how it became smarter. For doing this learning on 10 million books, it requires energy that is equivalent to 100,000 households, the annual energy consumption of 100,000 households. So it requires a lot of energy, it requires a lot of data, and it generates a lot of CO2. The amount of CO2 that is being generated by these LLM models, let's say typically 100 billion parameter models, to train them, it generates, let's say, 50,000 metric tons of CO2, which is equivalent to 500 cars running for their entire lifetime. So there's a big footprint of CO2, energy consumption, and data consumption for these large language models and generative AI. For spatial data to be in particular, it occurs in a lot of different forms. It occurs in a lot of different formats: civil engineering, environmental engineering, oil and gas, defense, agriculture, logistics, operations, retail, all these different sectors, they use different forms of spatial data. Some spatial data is in form of satellite images. Some of them are in form of LiDAR. Some of them are in form of traffic data, GPS data, location data, routes. Seismic map is an example of a spatial data. Plenty of times on top of your spatial data, there'll be a temporal component. So these data sets are coming in different formats from different sources with different resolution. And to combine all these data together for processing them carefully to extract information is always challenging. Spatial data is high dimensional. Being a high dimensional data, to create good generative AI models, we need a lot of data. We need a lot of training time, a lot of GPUs, and as soon as you increase the number of GPUs, you start increasing the carbon footprint, the energy footprint of such tasks. So with that, Yusuf, we can look into the questions if there is any from the audience, or else we can discuss a little more.
Yeah, I think there's a question here from LinkedIn. The question goes to us: I can see data summarization is useful for WRFM. For additional production from existing assets using multidisciplinary data, what challenges with data need to be tackled prior to applying Gen AI?
Yeah, so especially from a spatial data point of view, as I mentioned, resolution, different formats, mismatch of the data to kind of bring them together, stitch them together in time, in aerial extent is always a challenge. So some strategies to overcome these challenges with spatial data. Number one, data augmentation. Whenever we have spatial data, plenty of times mirroring them, rotating them helps us increase the data set size. It helps us to train our models better. So data augmentation is one. We have to be very focused on data cleaning and data pre-processing. Yusuf mentioned something called transfer learning. What is the use of transfer learning? You take a source model. The source model has seen enough data. You take it to a new condition, to a new aerial, to a new area of investigation. There you don't have enough data. So for those cases, you take your source model and train it, fine-tune it, perform feature extraction on it. That's an example of transfer learning, which can help you overcome data limitations in terms of quantity or sometimes in terms of quality. We need a lot of compute. We need a lot of cheap energy. As long as we have access to a lot of compute, cheaper energy, training these Gen AI models on large data sets are possible. And if you look at the architecture of these generative AI methods, plenty of times we have to apply strong regularization. With strong regularization, we ensure that these Gen AI don't hallucinate. They stay focused. They give us meaningful results. Regularization can occur in form of dropouts, weight decay. Plenty of times there is a human in the loop for reinforcing the network to generate sensible, reliable results. So these are some ways in which we can overcome the challenges of data.
Yeah, thank you so much, Dr. Sid, for your for the response to the question. I think that's the only question we have here. So if you could just as a roundup, just give us a few more examples on how Gen AI contributes to the innovation and problem solving in engineering projects generally.
Yeah, so for engineers, what I'm seeing a lot is creating new materials. That is one area where I see a lot of Gen AI uses. There's a material called MOF, Metal Organic Framework. It's a combination of an inorganic entity, an organic entity, along with something linking them. So this is a pretty complex structure. You can create such structures to act as filtering system, things that can filter out impurity from water, things that can filter out CO2 from gas. So to create such complex structures with specific properties, with specific cost in mind, that's where Gen AI is coming into picture. There's a large database of material properties. It's not possible to experiment on each and every combination. So Gen AI can learn from this material databases. It can learn from simulated data. molecular dynamic simulation, DFT simulation. And by combining all that, it can create new structures with specific properties that can hopefully address your needs. Let's say your energy transition needs, or a monitoring need, or some kind of a material construction need.
Yeah, thank you so much for sharing your knowledge with us today and for creating time to speak with us today.
Thanks for listening to the SPE Live podcast. For more content, visit the SPE Energy Stream, the industry's digital pulse, at streaming.spe.org. If you enjoyed today's show, don't forget to subscribe and review. Join us next time on the SPE Live podcast.